Bismillahirrahmanirrahim. Let's start our next topic in heat and mass transfer course. The topic that we are going to start is chapter number 12, radiation, process and properties. So in fact we had gone over an introduction to radiation back in chapter number 1. So kindly go over that portion of radiation so that you can have a basic understanding of radiation. We will now be dealing with chapters 12 and 13. Chapter 12 deals with the process and properties of radiation, and it does not deal with the heat transfer, with the radiation heat transfer. Rather, it is chapter number 13 which deals with radiation heat transfer. But in order to understand that, we must first look at several related process and properties. We would be discussing some of the topics that are listed over here. So the topics include radiation spectrum, radiation intensity, and solid angle, spectral radiation, spectral emissive power, and some other topics which we will go over in chapter number 12. Okay, we start with solar radiation. As discussed before in chapter number 1, that radiation heat transfer is a phenomena which takes place due to electromagnetic radiation, and electromagnetic radiations are those that do not require any medium to travel, so they can even pass through vacuum. So it is not only the sun is not the only object which emits radiation. Any object, as discussed before, which has a temperature which is at a temperature above 0 Kelvin would emit radiation. So any object around us, such as tables, such as walls, such as car, anything which is at a temperature above 0 Kelvin will emit radiation. Large or small in quantity, that is something else. That is related to its temperature, as discussed before, because E is sigma T4 or sigma epsilon T4. So emissive power is directly related to the temperature of the body. The higher the temperature of the body, more would be the radiation emitted out of it, means more would be its emissive power. And E over here has units of watts per meter square. All those things have been discussed in chapter number 1. So kindly go over that stuff before you start chapter number 12. Now over here are shown some components of solar radiation. Over here we can see three types of radiation over here, which are direct, diffuse and reflected. So direct radiation is that solar radiation which reaches to any surface directly, if this is the surface. Diffuse radiation is one which is scattered, which gets scattered. So it was going somewhere else, and when it hit the clouds or suspended particles in the air, so their direction was changed, and then it ultimately reached this surface. So that radiation will be called as diffuse radiation. And then there is third type of radiation which is reflected off the ground. So it did not hit this surface. In fact, this radiation did not hit this surface directly or indirectly. Rather, the radiation first hit the ground, and it was then reflected off the ground, and then it reached the surface. So if this is the surface, so the radiation that it will receive would be the sum of direct and diffuse and reflected. Sometimes the reflected component is very small, and some people neglect it under certain circumstances. It would depend upon the reflectivity of the ground. Over here, this is the same diagram. This is in fact a different diagram showing the same terms. We can see the direct radiation over here, which is coming directly from sun onto this surface, and then we have got this diffuse radiation. It was initially going in some other direction, and it was scattered, We then have this reflected radiation. So the radiation first hit the ground and it was then reflected off the ground onto the surface. And the solar radiation outside the atmosphere is called extraterrestrial solar radiation. Of course, extraterrestrial solar radiation would be more as compared to the radiation that will reach the ground, because of course extraterrestrial is near to the sun relatively. So these are all the solar radiation components. Over here, just to give you an idea that direct radiation is also called beam radiation. So whether we say direct or beam, we talk about the same thing. And this diffuse radiation is also called sometimes as indirect radiation. And with the one which is reflected off the ground or of the sea is called albedo. So and then it may get scattered and then it may reach the surface. That surface may be a photovoltaic panel which directly generates electricity, or it may be a heating solar. It may be a solar water heater or any other fluid heater which would not generate the electricity directly. Rather, they are utilized to heat up any heat transfer fluid. So those are the components of solar radiation, and not for any other normal radiation. Now here are we being shown the radiation spectrum. Over here the radiation spectrum means or rather it refers to the fact that there are various types of waves having different wavelengths, and you can see over here that the wavelengths in fact vary from a picometer 10 to the power minus 12 meters to almost a kilometer. So the wavelength may be as small as a picometer and it can be as large as a kilometer. So over here in the small wavelength region, we have got cosmic rays, we have got gamma rays, we have got X-rays. So since their wavelengths are very small, they can pass through any medium very easily. They can therefore pass through any medium very easily. Whereas over here we see some broadcast band waves and radio waves and radar waves and microwaves. So these are towards the relatively larger wavelength region, and those are towards a relatively shorter wavelength region. In here in between we see this colorful band, and this is what we call light. This colorful band is what we call visible light. So visible light is that radiation which a human eye can see without any external aid. Visible light is that radiation which a human eye can see without any external aid. Of course, some other radiations can be seen using external aid such as night vision goggles, but that would not be called as light, because light is that radiation which is visible to human eye without any external equipment. Now from 9th class or from matriculation classes, we used to remember this band with the word VIBGYOR, VIBGYOR, and VIBGYOR stands for violet, indigo, blue, and then green, and then yellow and orange, and in the end R is for red. So violet would have less wavelength as compared to red, because violet is on this side and red is on higher side. The wavelength of violet light is about 400 nanometers. 400 nanometers means 0.4 micrometer. 0.4 micrometer. Some people take it as 400, some people take it as 380. That is fine. Whereas the wavelength of red light is in fact 700 nanometers. So 700 nanometers would be zero point 0.7 micrometers. So some people take it as 700, some people take it as 710, 720, and that is fine either. So this is the radiation spectrum, means wavelengths can be as small as having waves can be as small as having wavelengths of a picometer, and waves can be having wavelengths as large as a kilometer. So this is the total radiation spectrum. Now now the question is whether all the bodies emit all kinds of wavelengths. The answer is no. Rather, it would depend upon the temperature of the bodies. Lower temperature bodies would be emitting radiation having wavelengths of a narrower region, whereas the bodies which are at higher temperatures would be emitting waves having wavelengths of a broader region. For example, if there is a body at, let's say, 30 or 40 degrees Celsius, it might only be emitting a little bit in the infrared band. But if the temperature of the body is, let's say, 1000 degrees Celsius or 1500 degrees Celsius, then it would be emitting in a larger band, in a broader band. So the type of the radiation emitted in fact depends upon the temperature of the body. This is the same diagram or similar diagram from our book. It is figure 12.3 of our book in Cropper and Dewitt, where again we are being shown gamma rays, X-rays, ultraviolet rays, infrared, and over here is also being shown the thermal radiation portion. So the thermal radiation portion is this portion which ranges from about 0.1 micrometer to about 100 micrometer. This is the thermal radiation band. And then we have the microwave and other types of waves shown on the previous page, such as radar waves and broadcast band waves. Relatively easier stuff when we talk about the components of incident radiation. If this is the radiation which is being incident on any surface, so what happens with that incident radiation which falls on any surface? See, a part of it may get absorbed, a part of that incident radiation may get absorbed, a part of it may get transmitted if it is not opaque surface, if it is not an opaque surface, and then a part of it may get reflected. So the total radiation would be dispersed, would be distributed in three parts. One part of it may get reflected, one part of it may get absorbed, and one part of it may get transmitted. The amounts of the radiation transmitted, absorbed, and reflected would depend upon those properties of the surface, which are absorptivity, reflectivity, and transmissivity. Absorptivity is simply a ratio of the radiation absorbed over the radiation which was incident on the surface, means G absorbed over G if we call G as the incident radiation. And then reflectivity is the radiation which got reflected out of the total incident radiation, so it is a ratio of G reflected over G. And similarly, transmissivity is a ratio of the radiation which got transmitted on the other side over the radiation which was incident on the surface, means G transmitted over G. So therefore G absorbed plus G reflected plus G transmitted would be equal to total incident radiation G, and they all would have units of watts per square meter. So if we divide throughout by G, so G absorbed by G would become absorptivity alpha, G reflected by G would become its reflectivity, means rho, and G transmitted over G would become its transmissivity, means tau. So and G over G would become 1. It means that alpha plus rho plus tau is 1. Over here it's figure 12.5 of our book, and it talks about what we were discussing on the previous page to a certain extent. See, what does it say? It says it is a semi-transparent medium, and over here we are talking about an opaque medium. Now in the semi-transparent medium, what is happening is that the radiation is coming in. It is called radiation, or it is also called irradiation. Right? What is irradiation? Irradiation is the rate at which the radiation is being incident upon a surface per unit area. So again it would be watts per square meter, right? So out of this incident radiation, one portion will get reflected, a part will get absorbed, and a part will get transmitted on the other side. This is exactly what we were discussing on the previous page. So total G is G reflected plus G absorbed plus G transmitted. Whereas over here we are being shown a different phenomena. More than opaque medium. For an opaque medium, what will happen is that the transmission would become zero. Transmission of that particular wavelength that we are interested in would become zero. But over here, more importantly, what we are discussing is a term called radiosity. Now, what is radiosity? See, there is something that we call emission, or rather emissive power. Right? What is emissive power? Emissive power is given as sigma T4 for a black body, and it is given as epsilon sigma T4 for a real surface, where E is its emissive power, epsilon is the emissivity, which has a value of 1 for a black body, sigma is the Stephen-Boltzmann's constant, and T is the temperature of that surface, whatever surface we have. So E is emissive power, means emissive power is in fact a measure of the amount of radiation which is being emitted by a body, and that emission is related to its temperature. Kindly note, it is very important sentence that the emitted radiation is related to the temperature. The lower the temperature of the body, lesser would be its emissive power, and the higher the temperature of the body, then larger or more would be its emissive power in watts per meter square. Now, so this emission is due to the temperature. This emission is due to the temperature of the body, of the surface. Now, it is quite possible. So even if there is no irradiation, emission would be taking place. As long as the temperature of the body is above 0 Kelvin, it will keep on emitting radiations. As long as the temperature of the body is above 0 Kelvin, it will keep on emitting radiations. Right? So emission does not depend upon irradiation. So now if there is a certain radiation falling on a surface, which was as it was taking place over here, so a part of it may get absorbed, a part of it may get transmitted, and a part of it may get reflected. Now our focus is on reflection. So depending upon the reflectivity, a certain portion of the incident radiation will get reflected. Now if we talk about the radiation which is leaving, a surface, so now the radiation is leaving the surface due to two attributes. One is the radiation which is leaving the surface due to the radiation emitted, which is due to the temperature of the body, and the other radiation is that radiation which is being reflected, and that is dependent upon that is due to the incident radiation. If there had not been any incident radiation, then there wouldn't have been any radiation that would have had reflected. If there hasn't been any incident radiation, then there won't be any radiation which will get reflected, right? So incident radiation will get absorbed, it will get transmitted, and it will get reflected, right? So now the sum of the radiation which is leaving a surface would be due to the radiation emitted by the surface and would be due to the radiation reflected by the surface. So the total radiation leaving a surface is what we call a radiosity, which is the sum of the radiation emitted, which is due to its temperature, and the radiation reflected. So radiosity is the rate at which the radiation leaves a surface per unit area, right? And it would be E plus rho times G, where rho is the reflectivity and G is the total incident radiation. So rho G is equal to G reflected. Now we are going to discuss a term which is called radiation intensity. And over here you can see a hemisphere, half of a sphere, just like igloo. So it says consider an area dA emitting radiations. So over here this is the dA emitting radiations and surrounded by a hemisphere of radius r, and is surrounded by a hemisphere of radius r. The radiations that will leave this particular object will be fully intercepted by the hemisphere, and we are being shown one patch over here, right? We are being shown some angles such as phi, such as theta. If you recall, we have gone over phi and theta in chapter number 2, where we were dealing with spherical coordinate systems, and I had shown you the two angles with the help of a cricket ball and also with the help of igloo. So you can refer to that particular lecture to understand what are those two angles. Over here, what is it that we are trying to understand? What are we trying to discuss over here? See, the thing is that if consider this as body 1, consider this as body 1, right? It says 1 over here, and consider this as body 2. Now if we are interested in the heat transfer between bodies 1 and 2, if we are interested in the heat transfer between bodies 1 and 2, so what is so special to discuss over here? See, the thing is that when the radiation will leave body 1, it will not only be incident on body 2, rather the radiation which will leave 1 will go in this direction, it will go in this direction, it will go in this direction as well, and it will go in this direction as well, and it will go in this direction as well, which will be incident on 2. So the radiation which is leaving 1, the whole radiation which is leaving 1 is not being incident upon 2. So when we would be considering heat transfer between bodies 1 and 2, then only that radiation which is leaving 1 and is being incident upon 2 should be taken into account, because that is that radiation which will play a part in heat transfer. This radiation which is leaving 1 but it is not being incident upon 2, this radiation which is leaving 1 but not being incident upon 2 has nothing to do with the radiation heat transfer between bodies 1 and 2. That radiation has nothing to do with the radiation heat transfer between bodies 1 and 2. So we are talking about radiation which is leaving 1 and is going in this particular direction. That radiation is called radiation intensity. So when we say radiation intensity, the word intensity refers to the radiation moving in a particular direction. And what would that particular direction be? In fact, that particular direction would be the angle between those two bodies would be the angle between 1 and 2, right? So first of all, try to understand what is meant by radiation intensity. Radiation intensity means the radiation moving in a particular direction. And why would we be interested in that particular direction? Because that particular direction would lead to body 2, and we would be interested in the heat transfer between body 1 and body 2. And since the radiation which is leaving 1, the total radiation which is leaving 1 is not being incident upon 2, so we need to find out that fraction of radiation. We need to find out that fraction of radiation. Fraction is important over here. We need to find out that fraction of radiation which is leaving 1 and is being incident upon 2, because that fraction will take part in heat transfer between bodies 1 and 2, and the other radiation which is leaving 1 and is not being incident upon 2 has nothing to do with the radiation heat transfer between those two bodies. Now let's discuss over here a solid angle, an angle which is called solid angle. But before we start discussing solid angle, you would remember S is equal to r theta. You would remember S is equal to r theta, where S was the arc, r was the radius, and theta was this angle, right? Theta was this angle. So theta is the angle subtended by, theta was the angle subtended by this arc or arc length onto the center point. This is what we used to learn in our matriculation or 9th class material. Now over here, so it was an angle on a paper. It was an angle in 2D, two-dimensional. Now if we talk about a three-dimensional angle, and let's take the example of a cone, ice cream cone, which we and the kids eat every now and then. So let's take the example of an ice cream cone, right? So you may consider this as the ice cream cone which has been placed horizontally or at an angle, right? So over here, this is the point where the cone ends at. So you may take it as the center, right? So if we talk about this angle, now this angle will not be on paper, rather it will be a 3D angle, because it will be in space, right? This angle is called solid angle. So this solid angle, which is being represented by omega or d omega, d would be for infinitesimally small solid angle, is something similar to theta. This omega is in fact something similar to theta. So theta was the angle over here, omega is the angle, omega is the solid angle. Theta was the angle subtended by this arc. So what do we have on the other side of the cone? We have that wrapper which we take off and then we start reading the cone, right? So over here it is not an arc, rather it is an area. It is an area. So theta is the angle subtended by an arc, and similarly solid angle would be the angle subtended by an area. So theta is the angle subtended by this arc over the center point. Similarly solid angle omega is the angle subtended by this area onto the center. Now what is this angle? Theta. What is this angle? Theta. What is this angle? Theta as well. What is this angle? Theta. All those are theta. So similarly this solid angle or the solid angle made over here or the solid angle made over here or the solid angle made over here would all be omega, would all be having the same value of omega. Just like if this is a 30-degree angle, so every angle, no matter wherever you draw it, would be 30 degrees. So this angle would be having the same value as we move along the axis of this cone. Now why are we discussing this solid angle? Now consider that we have placed a body, at the center, and this is body 1. I am going back to over here. See, we had two bodies, 1 and 2. So now we are having two bodies. This is body 1 and consider this as body 2. Now if we have this as body 2, so again if we are considering the heat transfer between bodies 1 and 2, so we need to find out that fraction of radiation which is leaving 1 and is being incident upon 2. So which radiation will leave 1 and it will be incident upon 2? It would be that radiation which will pass through this particular solid angle, which will pass through this cone angle, right? And that radiation would be termed as radiation intensity. That fraction of radiation would be termed as radiation intensity. So first of all, the solid angle is this area over r square, right? Because it was the arc length, S was the arc length over r. So there wasn't any units of theta. It is in it is in radians and gradients. And over here similarly solid angle would have area in the numerator, right? So when it would have area in the numerator, it cannot have r in the denominator. Otherwise the units of area over r would be that of length, which would not be angle, right? So over here if we have got area in the numerator, then we would have r square in the denominator, and the units of solid angle are steradians, just like we have got degrees and radians and minutes and seconds in case of angle. In case of 2D angle, the steradians are the units of the solid angle. And you can see over here that it says that although radiation propagates from dA in all directions over the entire hemisphere, because from dA1 the radiations would be leaving and it would be going on to the entire hemisphere, but only a part which falls within the solid angle subtended by that element will reach that element. That element means the top of the cone. This is body 2. So therefore you would have realized by now that radiation intensity and the solid angle are two very closely related parameters. So the radiation emitted in any direction is defined in terms of radiation intensity. In any direction means in any particular direction. In any particular direction. And why we would be interested in that particular direction? Because the second body would be there in that particular direction. Radiation intensity by definition. So this is the concept of radiation intensity. Now this is the definition of radiation intensity. It is defined as the rate of the heat flux emitted by it per unit projected area. Projected area means that area which was dN normal to the direction of radiation per unit solid angle. Per unit solid angle. So this is how IB5 is given. IB5 means in fact there are various letters that are used to represent radiation. For example, E is the emissive power, which have got the units of watts per square meter. G is also used to represent radiation. Some people use it to represent solar radiation, but that's fine. Which has also got the units of watts per square meter. Then we have got J that we just discussed. J is radiosity, having the same units of watts per square meter. Over here I would refer to radiation intensity, and B would refer to black body, and phi would refer to a particular angle, to a particular direction. This is what IB5 means. So what we do, so over here it says that if EB represents the total energy per unit area radiated in all possible directions, then it would be total hemispherical or emissive power. See if we integrate I B phi over all phi's, over all directions, over the complete hemisphere, what do we get? What do we get? If we sum up all the radiations which are being, if we sum up all the radiations which are being emitted out, what do we get is the total radiation emitted by the body, right? So that would be equal to EB or sigma T4. That would be equal to EB or that would be equal to EB means sigma T4, emissive power of a black body. Now, so it may be phi, or it may be theta, or it may be any other angle that you want to write it with. Now, the second type is spectral emissive power. So what is spectral emissive power? First of all, try to understand what is the physical meaning of spectral emissive power. See, we have two things: radiation intensity, number one. Number two is spectral emissive power. What was radiation intensity? Radiation intensity was the radiation moving in a particular direction, right? Now, so that was related to direction, that was related to angle. Spectral emissive power is related to the wavelength. Spectral emissive power is the emissive power in a particular wavelength band. Now let's take a look at the definition. The definition says that spectral body emissive power, so it would be a type of emissive power. It is the amount of energy, radiation energy emitted by a black body at an absolute temperature T per unit of time. So energy per unit time would make it watts. Per unit temperature means per Kelvin, right? Per unit surface area means watt per square meter, and per unit wavelength about that particular wavelength lambda. Per unit wavelength about that particular wavelength lambda, and this is the expression. But in this expression there are several terms such as C1 and C2, and lambda is the wavelength, T is the absolute temperature, where C1 is this constant value and C2 is this constant value, and C0 is the speed of light. That is fine. But see, we should rather focus, we should be focusing on the physical significance of spectral blackbody emissive power, rather than getting confused or rather than getting lost in this expression. See, as I have just told you that what is spectral emissive power. Spectral emissive power is the emissive power around a certain wavelength. Means, let's say there is a body which is emitting gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwaves, radar waves, radio waves, and broadcast bands. So we have a body which is at a very high temperature, and therefore it is emitting all the radiations, or 4 or 5 types of radiations. Now, let's say we are only interested in this band. We are only interested, let's say we are only interested in the visible light band. Means we are not interested in finding out how much that body is emitting in the ultraviolet region, or in the X-ray region, or in the infrared region, or in the microwave region. We are only interested in finding out that if we have a body in hand, then how much of that surface, how much of that body is emitting in the visible band. And why would someone be interested in it? For example, if you are Philips, if you are any other tube light or bulb manufacturer, so now the objective of the product is to provide visible light, which will aid in seeing the objects around us, right? So what wavelengths would be of help to us? What wavelengths would be of interest to us? What wavelengths would in fact help us illuminating the objects? It is that band which we call visible light, 400 to 700 nanometers. So that is why if we have an object in hand, if we are, let's say, Philips, we would be interested in finding out that how much radiation which is being emitted by the object lies in this visible band, because that will be of use for our product. Similarly, if you are, let's say, LG or Dowlands and you are making the microwaves. So then you will not be interested in finding out that how much that particular object is emitting in X-ray band or in ultraviolet band or in infrared band. Rather, you would be more interested in microwaves. Similarly, if you are an X-ray machine manufacturer, then you would be interested in finding out that how much of any particular material which you are using in your X-ray machine is emitting in this particular band, because this will, the emission in this band, in this particular band, will help us in the use of that X-ray machine, and any infrared and microwave and radar wave will not help us in the operation of that X-ray machine. So that is why people would be interested in particular wavelength bands for very obvious reasons that we have discussed so far. And the radiation in this particular band, in a particular band, for example in X-ray band, or for example in invisible band, or for example in a radar band, the fraction of or the radiation in those particular bands would be called as spectral emissive power. Spectral emissive power means emissive power in a particular wavelength band, in a particular wavelength band. And suppose that we have an object which is emitting X-ray, ultraviolet, visible light and infrared. Suppose it is emitting X-ray, ultraviolet, infrared and microwave, and not any other kind of radiation. So if we add up the radiation in X-ray band and the radiation emitted in the ultraviolet band and the radiation emitted in infrared band and the radiation emitted in microwave band, what do we get? We get the total emissive power. We get the total emissive power. Means that if we integrate this EB lambda, see over there in the intensity, what did we have? We had EB phi, because radiation is related to direction, whereas spectral is related to a particular wavelength. So if we integrate over all the wavelengths from 0 to lambda, over here 0 would refer to the X-ray wavelength, and this upper value would refer to the microwave, because it is not emitting, as we have just said, it is not emitting any radiation having wavelengths less than X-rays and more than microwaves. So therefore lower limit would become X-ray wavelength and upper limit would become microwave wavelength. And if we then integrate it with respect to lambda, what do we get? The total emissive power means EB, means sigma T4. So again, summarizing all the things, we have discussed radiation intensity and spectral emissive power. Radiation intensity is that radiation which is in a particular direction, and spectral emissive power is that radiation or is that emissive power which is about a particular wavelength for the reasons that we have just discussed.